What if everything we know about the universe is wrong? What if Einstein, the father of modern physics, was incorrect? These are the unsettling questions that emerged from a neutrino experiment in Geneva that challenged the very bedrock of our understanding: Einstein's theory of relativity. In this intriguing experiment, neutrinos, those ghostly subatomic particles, seemed to pull off a cosmic magic trick. They appeared to outpace light, sprinting 60 feet ahead over a 454-mile racecourse from Geneva to Italy. This astonishing feat, if true, pokes holes in the fundamental principles of relativity, the cosmic speed limit that declares nothing can travel faster than light. This revelation doesn't just rock the boat, it flips it entirely. It's the equivalent of finding a square wheel in a universe that's always run on round ones. If Einstein was wrong, what could this mean for our understanding of the universe? The thought of Einstein being incorrect might seem absurd, but let's explore what that could mean. If the theory of relativity is flawed, then the consequences are remarkable and far-reaching. Imagine a world where time travel isn't just a concept in a science fiction novel, but a commonplace reality. Imagine the implications for science and society as we know it. Beyond that, every scientific measurement we take for granted would require recalibration. The age of the universe, for instance, would need reassessment, throwing our understanding of cosmology into disarray. The distances to faraway stars, currently calculated based on the speed of light, would be thrown into question. Even the fundamental principles of electronics, which are deeply rooted in the theory of relativity, would need a second look. The implications are vast and mind-boggling, but before we jump to conclusions, let's consider the skepticism surrounding this experiment. While the results of the Geneva experiment are intriguing, they have been met with skepticism. Now, why might that be? Well, as with any groundbreaking experiment, it's crucial to consider the potential for systematic errors. In the case of the Geneva experiment, some have suggested that these errors may be tied to the calibration of the GPS system used. Here's a bit of irony for you. The GPS system itself is a real-world application of Einstein's theory of relativity. Since the satellites are moving relative to the Earth, the time on the satellite clocks runs slightly slower than the time on Earth. This effect, known as time dilation, is corrected for in the GPS system using the principles of relativity. So if there were any inaccuracies in the GPS calibration, it could have distorted the experiment's results. After all, if our measuring stick is off, even by a hair, our results will be skewed. And in the world of physics, even the smallest of errors can have monumental implications. It is also worth noting that the neutrinos in the Geneva experiment supposedly outpaced light by a measly 60 feet over a roughly 454-mile journey. That's an incredibly thin margin, and any minor systematic error could easily account for it. Historically, groundbreaking results have often been met with skepticism and careful consideration. Let's look at an example. In the world of physics, the Pound-Rebka experiment serves as a cautionary tale. Now, this isn't just some random story from the annals of scientific history, but rather a potent example of the potential for errors in delicate calculations, and the importance of careful consideration in interpreting groundbreaking results. The Pound-Rebka experiment, conducted in the late 1950s, aimed to test Einstein's theory of gravitational redshift. This is the idea that gravity can affect the frequency of light, causing it to shift as it travels from a lower to a higher gravitational potential. Pound and Rebka set up an experiment in Harvard's Jefferson Laboratory, using a source of gamma rays at the bottom of a tower and a detector at the top. Their results seemed to confirm Einstein's predictions to a T. However, they later found that their calculations had been skewed by a tiny, almost imperceptible effect: the temperature-dependent Doppler shift. When they factored this in, their results were even more accurate, tightening the experimental confirmation of Einstein's theory. This historical tale serves as a reminder of the intricate delicacy of scientific experiments, especially when we're dealing with the fundamental laws of the universe. It underscores the importance of scrutiny, of checking and double-checking our work. So while it's exciting to question the foundations of modern physics, it's crucial to remember that extraordinary claims require extraordinary evidence. Until further evidence is provided, Einstein's theory remains a cornerstone of our understanding of the universe.